Okay, welcome back. This is again Unit 21. As mentioned before, this is another part two of Unit 21. And in this part, we'll be discussing a little bit about quantum cryptography. So there's been a lot of current times. There's a lot of talk about quantum computers and how physics and photons have an impact on computing and data transfer, and quantum cryptography also relies on the similar process, similar concept. So basically it revolves around quantum mechanics, the laws of quantum mechanics, which provide fundamental laws of physics applicable to the behavior of particles. The particles that transmit light are called photons, and these photons are basically we are using these photons to transfer data. The direction of each photon that vibrates in is polarization. So basically, they are capable of vibrating in different directions, and these are known as polarization. A photon can be created with a specific polarization to represent a value for a bit. So basically what that means is that if I am, for example, sending this photon, it can either mean a 0 or a 1. So as opposed to conventional bit transfer, a bit is a bit. If it's a 1, it's a 1. But right now, if I'm transferring photons, I'm not transferring ones and zeros. What I'm transferring is photons. So these photons, okay, they basically can have more than one representation. That's why that's why it's so incredibly difficult to apply quantum cryptography. So basically what's happening is that if we allow for 4 possibilities for the state of polarization, there are 2 ways to represent 1 and 2 ways to represent 0. So basically this polarization, this vertical polarization, this is known, this can be used for representing 1, and this can be used for representing 0. Whereas the diagonally, this can be used, this diagonal direction can be used to represent 1, whereas this diagonal representation can be used to represent 0. Okay, when collectively, this direction and this direction, when combined together, they form this shape, this plus shape. Now this plus shape is basically known as the rectilinear filter. This is, it's actually written here as well, the rectilinear filter. So this plus sign is actually the rectilinear filter. So this filter can either represent 1 or 0. So if it's this vertical one, it's 1. If it's horizontal, it's 0. So basically, if these two representations are part of the rectilinear filter. On the other hand, this is known as the diagonal filter. So as you can see, this is the combination of these and these two combined. They form this sort of X multiplication sign, and this is known as a diagonal filter. So if my sender is choosing to send data 1 or 0, they can use either one of these, the rectilinear filters or the diagonal filters. So now let's consider this example. As you can see in this table right here, I can see that these values, these bit values are being sent. So 1, 0, 1, 1, 000, 1, 0, 1, these values are being sent. And based on the polarization techniques I'm using. Okay, so as we can see, this is the bits transferred 1, 0, 1, 1, 000, 1, 0, 1, and the sender has chosen these polarization filters when transferring each and every bit. Now, what happens is that the receiver, okay, by the way, the sender has chosen these filters at random. There is no system, it's just at random. So as you can see, as mentioned before, this rectilinear filter can create a 1 and a 0. So for 1, they chose this filter, and for 0, they chose this filter. So it's completely random. Okay, on the receiving side, the receiver will also choose filters for receiving these photons. They have to do that. Now, again, these filters on the receiving end will also be chosen at random. So there is just guessing it. So the receiver will at some point, there's a great chance, actually not a great chance, but a 50% chance that the receiver will at some point receive the right bits. So as you can see here, The filter they have chosen, the receiver, the filter they have chosen is the same as the filter that is being used when sending data. So as you can see here, the polarization filters used by the receiver are, this is wrong, this is different, this is reflected, but this is correct, in which case the bit value is confirmed. And if this is wrong, this is correct, this is wrong, this is wrong, this is correct, as same as the sender, and this is also correct. So again, there's a 50% chance that there is properly guessing it or not. Okay, so let's just look at what this table is elaborating on. The first row indicates the bit sent. Second row shows the basis of which the filter, the plus representing the one using vertical and the horizontal, and X is representing the diagonal pair. So rectilinear, by the way, the term for plus is rectilinear filter. So plus means I'm using rectilinear and the sender is using rectilinear, and the multiplication sign shows that the sender is using a diagonal filter. The sender chooses this bit pattern at random, also the polarization at which each value at random. So again, the bit pattern is random, the polarizations are also random. At the third row shows this one right here. That the third row is receiver's choice for the polarization. So again, this is at random. So as mentioned before, these filters are chosen by the receiver at random. Following the transmission, the sender informs the receiver. Now, basically what happens is when the data is received by the receiver, there's another communication between sender and the receiver. And in this communication, the sender is simply stating what polarization was being used by by the sender at that particular bit. So for example, when the sender sent this data, they used this sequence of filters. And when the receiver received the data, they use these sequence of filters. Now, when the sending and receiving is done, there's a second communication that takes place between the sender and receiver. And in which case, the sender and receiver simply discuss bit by bit what filter was being used by the sender, and the receiver will say what they used for receiving that bit. And if they are the same, then that is a confirmed value. So for example, the sender after sending the data, receiver after receiving the data, they have a separate communication, and the sender says that, okay, for the first bit, I use the rectilinear filter. The receiver says, no, I use diagonal. So, okay, this is not the same. Same thing goes with the next bit. Both are not the same, so it also ignored. Okay, now when we reach this bit over here, the sender says that I use the rectilinear filter here, and the receiver says, yes, I also use the rectilinear filter. So this value is confirmed. This is a proper data transmission. Again, a little caution here is that it isn't necessarily one, it could be zero as well, but still the filter is right. Okay, anyway, so the second is wrong, but this one is okay. So for this bit, the sender says I use diagonal, receiver says I also use diagonal, so this is also confirmed. This is wrong, receiver confirms this one, this value is confirmed, and this one also matches this one's. So now the thing is, let's just say, for example, there is a third person listening into this transmission, this second transmission in which both sender and receivers are discussing the filters being used. They are simply discussing the filters. The receiver, the unauthorized listener will have no idea of what underlying bits are being used. They will simply, there's no discussion of bits. So basically the sender is not saying I sent one, did you get one? No, that's not happening. That's not happening. They are simply discussing what filter was used. So unauthorized listeners, well, even if they are listening into this transmission, this second transmission, they will not be able to guess. They will not be able to understand what bit is being used at that particular time. Okay, so now my receiver has confirmed 4 bits that are using the same filter as my receiver. So this will become my key. So this is my shared secret, or this is my key. This is my confirmed key, which will be used in further transmissions between my sender and receiver. Now again, as mentioned before, there's a 50% chance that my user will not be able to receive the correct data. Why 50% chance? Because even though my filter is correct, it isn't necessarily that if using plus the sender actually did send one. There's a great chance that they actually send zero, but there's a 50% chance that I might get the correct values, and there's a 50% chance that I might not. So again, but the key is confirmed. The sequence of filters that are being used that are confirmed, and this filter will be used in further transmissions. Okay, now basically what we did here is that we addressed the key distribution problem that we discussed in early Unit 21 with using symmetric encryption. And we said that if we want to use the same key for sender and receiver, there's a problem that we have to face in which I have no means of sending the key to the receiver. And if I use the same channels that I'm using for data transmission, my unauthorized listener will be able to hear in the data transmission as well as the key itself. And so basically, there's no purpose of defeat. There's no purpose of encryption whatsoever. So that is the key distribution problem. Now over here, I have basically addressed one of that key distribution problem very effectively, in which basically I am simply comparing the filters. Earlier, we saw how a key might be transferred using symmetric key encryption for subsequent use in symmetric key encryption. Using asymmetric, we use it asymmetrically. So basically what we did was we encrypted the symmetric key using the public key, sent it to the intended recipient. The intended recipient using their own private key decrypted it, and they have the symmetric key that we both used. That was one method. Now this is a more effective method. Now, quantum key distribution offers an alternative for key transfer. The key is still to be used in the normal way. For example, this is the key we generated right here. The advantage of quantum key distribution is that the transfer does not involve defined values. There's no ones and zeros being transferred, so it's even more secure. It just uses photons. That means the main drawback. So basically, I'm not sharing any ones and zeros, so it's more secure. And if there is some, for example, an unauthorized user who's trying to listen into this transmission, they will not be able to understand what transmission is being taking place. And even if they do try to receive the data, the laws of quantum physics will cause that data to change. Now we'll be looking into that in a bit. But basically, it's extremely difficult for any unauthorized user to listen into that transmission. Now, however, there are drawbacks regarding quantum cryptography. First of all, the main drawback of quantum cryptography is that it cannot be implemented using standard quantum communication media. So currently, our entire communication setup that we're using for internet, that becomes useless whenever we want to apply quantum physics and these laws of physics for this data transmission. So we have to have dedicated special purpose quantum channels between the sender and receiver for this technique to be effective. The cost of providing this are very high, so routine use is unlikely yet. But who knows, in the future we'll be using this technique. So that's one very big disadvantage of quantum key distribution. But nonetheless, it is a very intelligent way. It's a very secure way of transmitting the key between the sender and receiver. So this handles the key distribution problem very effectively. Okay, now let's look at different scenarios in which we have an unauthorized user and we're using the quantum cryptography method for securing data. Now, assuming that this is my sender and this is my receiver. My sender uses the rectilinear filter and sends a 0. Okay, now let's assume that quantum channels exist. This is down in the distant future. Quantum channels exist. And I have used a rectilinear filter to send 0. Now, this unauthorized user, since quantum physics involved, this unauthorized listener will also be can listen to this data, can receive this data, but it too will be using these filters to receive these photons. So these photons will be received using these filters only. Now, let's just say that this unauthorized user ends up using the wrong filter. So it ends up using the diagonal filter. Now, what that does is that it causes the data to change. So basically that 0 would become a 1 because it went through the wrong filter. Now, my receiver is expecting a 0 because it's using this filter and it's an agreed upon filter. So I remember that we created a key before. So that means these filters were tallied beforehand. These filters were tallied beforehand. So when I'm actually sending the data, the bit that using a rectilinear filter, the sender will be using and the receiver will be using the same filters. But the unauthorized user is still guessing it. He does not know what filter is being currently used. So randomly, at random, let's just say that they use the diagonal filter, because of which when that data is received by this unauthorized user, it will change the photon, the direction, the rotation of the photon will change because of this filter, due to which I'm expecting a vertical, I'm expecting a rectilinear 1 or 0, because of which it will be changed. And there's quite possible that if it's 0, it will become 1, or if it's 1, it becomes 0. And that's what's happening here. Now, since I'm receiving the wrong data, and that bit I just received will be ignored because it's wrong. Not only will I ignore it because I know it's wrong. Why do I know it's wrong? Because I'm using rectilinear filter, the receiver is using rectilinear filter, the sender is using rectilinear filter, and a 0 should have been a 0. But since it's a 1, that means that there has been some change in between. Now, this does two things. First of all, it alerts my receiver that not to trust this bit. Secondly, it also alerts the receiver and the sender both that there is some authorized listener that is listening into the transmission, because of their listening, it causes the data to be changed. Now, this is something different to current data transmission channels that they're using. So unauthorized user may be listening into the transmission, and both sender and receiver will not be able to know, will not be able to figure this out, because the unauthorized listener will listen to data and this will not cause any change to the data. However, in quantum cryptography, the unauthorized listener, if they end up using the wrong filter, will cause the data to change altogether, because of which my receiver will be alerted automatically and they will know instantly that there is some unauthorized listener in between our transmission, and they can take the necessary precautions there. And how did they know? Because they were expecting certain value and they received another value, hence proving that there is some authorized listener here, and they probably have guessed, the wrong filter. Again, this too is random. They have randomly guessed the wrong filter, because of which the data has changed. Since the key has been agreed upon before, it will become evident that someone is listening into the transmission. So at particular bit, the key says 1 and it should be 1. Sorry, if the key is setting a rectilinear filter, the receiver is also using rectilinear filter. But since the authorized user randomly guessed the diagonal filter, it changes the data, and it will cause the receiver to be alerted that this data should not be trusted, and this transmission is also compromised. Second scenario is that, let's just say that the unauthorized listener did, however, randomly, at random, guessed the filter properly. So in this case, for a particular bit, I was using 1 and the unauthorized user was using plus. And the receiver, for example, just at random, let's just say at random, the receiver at random selected the wrong filter. So what happens is, in any case, if I get a 0 from here, this 0 will remain unchanged because it's passing through the same filter. However, I'm expecting a 1 here because I at random chose the wrong filter, and because of which that data will still be ignored. So there's a 50% probability that the receiver will receive the wrong data, in which case this bit will be considered wrong. So now, since I at random chose the wrong filter, I was wrong about choosing this filter. And this is, by the way, initial stages. This data will still be ignored. Now, this is, by the way, taking place here. So let's just say this data, when being sent to the what you call it, receiver, and say unauthorized user is listening into this, and they say the unauthorized user gets the same filter as this one. But since I chose the wrong filter, I will in any case ignore that bit because it turned out to be a different bit. So that's another way how this quantum cryptography is making sure that the unauthorized listeners don't end up with the right. So this bit gets ignored nonetheless. So anyway, in the following lectures, we'll be looking into some symmetric encryption techniques more importantly, the simple data encryption method, SDES. And we also look at the asymmetric encryption technique, the Revest-Shamer-Edelman RSA method in separate videos. So stay tuned for those as well. So anyway, take care.